In this video, I'll be analyzing phi, okay, the golden ratio. Say I have a line segment, right? It's divided into two different line segments. Okay, one that has length A and another has length B. And it has the property that the ratio of the small one to the big one is going to be the same thing as the ratio of the big one to the entire length. Okay? Or in other words, the ratio of the big one to the small one is going to be equal to the entire thing to the bigger one. Okay? Now what I'm going to do is I'm going to expand that out into a over b plus 1, right? I can do that because I can split up that into a over b and plus b over b, and b over b is 1. And let's call this value phi, okay? Right there is 1 over phi, so I get phi is, well, let me write it out. It's going to be 1 over b over a, right? Because a over b is 1 over b over a. So that means phi is plus 1. Is 1 over phi plus 1. Okay, I'm going to write it instead as 1 plus 1 over phi. Okay? Now, what you can do with this is you can plug in for phi right there. Phi is 1 plus 1 over phi. So that's going to be 1 plus 1 over 1 plus 1 over phi. Okay? Oh, but I can plug in for phi again, which is 1 plus 1 over 1 plus 1 over 1 plus 1 over phi. And you can imagine continuing that on infinitely until I get 1 plus 1 over 1 plus 1 over 1 plus 1 ... Right? Okay, so then let's go back to this. Don't worry about that. So let's multiply this by phi on both sides. So I get phi squared equals phi plus 1. Phi squared is phi plus 1. And then I get phi squared. First, let me look at something interesting about this. I get phi is the square root of phi plus 1. Or I'm going to write it the square root of 1 plus phi. Okay? Oh, but what's phi? It's the square root of 1 plus the square root of 1 plus phi. But phi is the square root of 1, and you can imagine continuing that on forever, and you'd get phi again. So for some reason, this infinite fraction and that infinite radical are equal, and I'll formalize this in a bit. And then I get phi squared minus phi minus 1, right, equals 0. Then we can use the quadratic equation, which gives us phi equals 1 plus or minus, and it can't be minus, I'll tell you that, b squared minus 4ac, that'll give you 5 over 2a, which is just 2. And there we have it. Okay? So let's go ahead and formalize this a bit. What do we mean by an infinite fraction, and what do we mean by an infinite radical? Okay? So by an infinite fraction, if I have a1 plus 1 over 1 plus a2 plus 1 over a3 plus 1 over a4, and so on, right? Then I'll define this to be equal to a1 plus a2 over 1 plus 1 over a3 plus ... until I get an minus 1 plus 1 plus 1 over an, okay? So we're going to have that infinite fraction. And so we're going to take the limit as n goes to infinity of that. So we just cut it off right when we get to an, and we look at the limit as n goes to infinity. So let's look at a specific example. If I'm going to do the limit as n goes to infinity of 1 plus 1 over 1 plus 1 over 1 plus, continue that down until I get 1 plus 1 over 1, right? There. Okay, what's 1 plus 1 over 1? Well, 1 plus 1 over 1 is going to be 1 plus, I'm just going to evaluate this bottom bit. That's going to be 2. And so I'm going to have 1 plus 1 over 2, right? That's going to be on the fraction below. And so I'm going to have 2 over 2 plus 1 over 2. So I get 3 over 2 there. Oh, but then I'm going to have 1 plus 1 over 3 over 2, which is going to be 1 plus 2/3, which is going to be 5/3. Continue that down. I'm going to call it an minus 1 over an minus 2, and you'll see why. Okay? I'll get to there, and then I'll do 1 over that, add 1, right? 1 plus it. But that gives me 1 plus an minus 2 over an minus 1. But that gives an minus 1 plus an minus 2 over an minus 1. Okay? Let's define an to be an minus 1 plus an minus 2. So then I get an over an minus 1. Right? So this really is going to be the ratio of an to an minus 1, where an is equal to an minus 1 plus an minus 2, where a0 and is equal to 1, and a1 is 1, right? That's what we started off with. 1 and 1 over 1. 1 over 1. That's the ratio we started with. That's the initial conditions, and this is the formula we have for getting the next term. This is the Fibonacci sequence. Fibonacci. Okay? So let's write this down. Okay? So we had that this 1 over 1 plus 1 over ... 1 plus 1 over 1, right? For n1s, sorry, 1 plus out front, n times n different fraction bars. This is going to be an over an minus 1, right? That's what we determined for an, and for an the nth Fibonacci number, nth Fibonacci. Okay? Isn't that cool? Well, now, if I want to evaluate the complete integral, I get that 1 over 1 plus 1 over 1 plus ... right? Which is phi, remember? It's going to be the limit as n goes to infinity of an over an minus 1 for an, the nth Fibonacci number. Okay, but we don't know if this actually is phi, remember? Because we don't know if this limit is really phi. We just kind of did a pseudo proof. But what we can do is use the fact that the limit as n goes to infinity of bn is going to be the limit as n goes to infinity of bn plus 1. Okay? Those two things, it's very easy to prove that these two things converge to the same value. Okay? So then, we get this is equal to the limit as n goes to infinity of an plus 1 over an. Right? Oh, but an plus 1 is going to be an plus an minus 1. And you can see that we can split this up into 1 plus an over an minus, 1 plus an minus 1 over an. This is what we're left with. And you can see this is exactly what we had for the phi. For phi, we had phi equals 1 plus 1 over phi, right? This is the same condition, right? But we have to make it formal. Okay, so let's subtract. Let's subtract it from both sides. So I get the limit as n goes to infinity of an minus 1 plus an minus 1 over an plus, minus 1 is 0, right? And then what you could do from there is multiply this limit on both sides, multiply both sides of this equation by multiply both sides of the equation by an over an minus 1, okay? So that's going to be 0 times an over an minus 1, okay? Oh, but 0 times anything is 0. And distributing that into the limit gives us the limit as n goes to infinity of, and then I get an squared over an minus 1 squared, right? Then minus, I'm going to do that 1, minus an over an minus 1, right? And then right there it's going to be a minus 1 equals 0. Okay, but what I can do is I can make this the limit as n goes to infinity of an over an minus 1 squared minus the limit as n goes to infinity of an over an minus 1 minus the limit as n goes to infinity of 1, right? But that's just 1 equals 0. Oh, but because squaring something is a continuous function, I can move those parentheses outside to get this, and you can see this is a polynomial in the limit as n goes to infinity of an over an minus 1, so this gives me the limit as n goes to infinity of an over an minus 1 is going to be a, or negative b, plus or minus the square root, we can ignore the minus, the square root of b squared minus 4ac, right there. And thus we've evaluated this limit, and thus we've evaluated this infinite fraction, and now we have our value of phi. And what I'm going to do is I'm going to very quickly do the same thing but with square roots, with the square root version. Okay, so now, what is the square root of 1 plus the square root of 1 plus dot dot dot? Okay, I'm going to define it to be the square root. It's the limit as n goes to infinity of the square root of 1 plus dot 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 plus the square root of 1. Okay, where we have n ones. Okay? Now, I'm going to rewrite this a little bit. This is going to be 1 plus the square root of 1 plus the square root dot 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 plus the square root of 1, right? Okay? So, what you notice here is right there, if I make this, get rid of that limit and call that Rn, you may notice that right in there is Rn minus 1, because that has n minus 1 ones. So this gives us that Rn is going to be the square root of 1 plus Rn minus 1, right? Okay, so this is going to be useful because we can do the limit as n goes to infinity of Rn to be equal to the limit as n goes to infinity of Rn plus 1, but Rn plus 1 is just the square root of 1 plus Rn, right? And then we can square both sides of this, right? The limit n goes to infinity Rn equals the limit as n goes to infinity of the square root of 1 plus Rn squared. But because these are continuous functions, I can move those squares inside, and then I get that the limit as n goes to infinity of Rn squared equals the limit as n goes to infinity of 1 plus Rn, correct? Now we subtract it over, you get the limit as n goes to infinity of Rn squared minus Rn minus 1 equals 0, and then you can distribute the limit into it. But it's very clearly obvious that Rn is going to be 1 plus the square root of 5 over 2, which is phi. And so, using rigor, we've proven that all of these are, in fact, by definition, equivalent to phi, the golden ratio.